Let's talk about 3.2. So we have an H, which is symmetric and idempotent matrix, aka projection matrix. And X is normally distributed 0 and n. Why don't I just do, I'll talk about D and E for you, and then I'll kind of start actually from 3.1 from the beginning, or actually from these problems. Okay, so you want to show, so we have mu, which is in the image of H. This actually isn't really relevant to the rest of the problem. So we have mu, which is in the image of H. We want to show that H mu is equal to mu. Okay. So remember, H is symmetric and idempotent. So that means that H squared is equal to H, and then also H transpose is equal to H. And we have that mu is in the image of H. Okay, so what does that mean? That means that there exists some vector, I'll just say V. Actually, I think they use V earlier in the problem. Let's use W. It looks too much like mu. C, D, E, what do I want to use? K, that's a fun one. It exists some vector K such that H K is equal to mu. So this is an equivalent statement. Mu is in the image of H, right? Is an equivalent statement that HK is equal to mu, right? And this, yeah. Okay. So we want to show that H mu is equal to mu. Okay. Well, there's a couple ways to do this. What we could do is we could say that you can multiply both these sides by H and get that H times H mu is equal to H mu, which is equal to mu. And that gives that, sorry, no, that's not right. H times HK is equal to H mu, which gives that H squared K equal to H mu, which implies that H, so this is from idempotency, we have that implies that HK is equal to H mu. And we also have that HK is equal to mu. That's it. Right? Yeah. Right? So HK is equal to H squared K is equal to H mu. H squared K is equal to HK, which is equal to H mu. HK is still equal to mu. Does that answer your question? Oh.
Does that mean that we take mu as a random vector?
So
and
mu
use
is
H2.
Yeah. Sorry, keep going.
And we can think of it like project the vector mu or the vector k onto some place.
Sort of. Okay, so the kind of like the theoretical idea behind this would be that H is a projection matrix. And so remember, a projection matrix always, for any subspace, you always can imagine it as like, what a projection matrix does is, if this is your subspace, it takes your vector, no matter what it is, let's call this mu, and it projects it downwards. And then this becomes H mu. So if this is H, then a projection matrix will always come down to H mu. Because we said that, but then mu is already in the image of H, basically. So what we're basically doing here is we're saying mu is in the image of H. So all we're doing instead is mu's already here. And so it doesn't do anything. So multiplying by H, this results in H mu still being the same. that's what's theoretically happening. But that's not really what the problem's asking for. The problem's saying, okay, prove it, right? Prove if H is some symmetric and idempotent matrix. Really, we're only using idempotency from what I can tell. That if mu is in the image of H, then H mu is equal to mu. Now, this actually holds for any subspace. So the reason that it actually holds for any subspace is just he wants you to show it sort of using the fact that it's idempotent, which is a lot easier, right? This is like a very easy case. So I said mu is in the image of H, and that the definition of being the image of H means that there exists some K such that HK is equal to mu, right? And then I went from there. So I started here and I said, okay, well, I need to, I have mu, but I also need H mu. So I'll multiply by H on both sides, which is allowed, right? And I get H squared K is equal to H mu. But then H squared K is equal to HK because it's idempotent, which we said before is equal to mu. And so then we have this chain of equal signs saying that mu is equal to H mu. And that's pretty much all you have to show. Showing it for a general matrix would be much more difficult. You know what I mean?
Yes, that's much clearer. Thank you.
Cool. Yeah, no problem. Okay, and then the next one, so you asked about E. So assume that one is in the image H and find the distribution of 1 transpose HX. Okay. So remember, X is distributed as normal, 0, 1, n. Hold on, let me grab the notes for this one. Oh, this is not my notes. This is for last quarter, geostatistics. I do not think you care about that. Unless you want to know about geostats. That's actually kind of what I'm doing research in. Okay, so this one is really similar to the ones before. So remember, a really core part of this whole thing, which I'll get to in a bit probably as well, is that pretty much the main thing you're going to be using this is the fact that if y is distributed as normal mu sigma, then ax plus y, ay plus b is distributed as normal a mu plus b a sigma a transpose. Oh my god. You won't see my beautiful face. This is the moneymaker up here. Okay. This is the moneymaker brain, you know what I mean? Got me this far. And my wit. Charming. Awesome. Like cool tie-dye t-shirts. Okay. So then for this, we have that X is distributed normally. Sorry, I know it's really annoying when I go back and forth. Normally as 0 I, I'll say IN. We want to find the distribution of 1 transpose HX. So we can just treat this like a matrix, right? So let's consider this our matrix. So this is A from the above problem. And so we can just replace all these A's with this, right? So to find what this distributed as, so that means that 1 transpose HX is distributed as normal. It's still 0, right? Because all these are going to be mean 0 if we're just multiplying and not adding anything. And then for this, we need A, which is 1 transpose H, sigma, which is IN, and then A transpose, which is 1 transpose H. And then this is really our answer, except we can just simplify this pretty easily. So notice how this kind of just goes away and we get 1 transpose H, 1 transpose H. Oh, sorry, this should be transpose. Transpose, and then just simplify this, which shouldn't be very difficult. And then does it have like a part B to it? No, not really, yeah. Oh, but you're saying assume that 1 is in the image of H. I don't know how that's relevant. Huh. Does that matter at all? Oh. Well, I mean, would it? Oh, yes, it will. Yes. Okay. So then you want to use the fact that, okay, from here, I don't want to give the answer, but use the fact that H transpose is equal to H, use the fact that H squared is equal to H, and use the fact that now we know from above, H times 1 is going to be equal to 1. And we know this one because of part E. Part, what was it? D? Part D. Sorry, it's hard when this is the one vector. This is from part D. And see what you end up getting. Does that answer your question? Maybe, maybe not. Okay. You can't, I don't know if you're trying to say something, but I can't hear you. So you can put in the chat if you need. But otherwise, that seems like it's pretty much parts D and E of this question. Any other questions? Okay. Oh, sorry, I just got kicked out just now. Thank you very much. Okay, let me know if you have anything else. Okay. You can leave if you guys need to. I know, Tayo, you might need to leave. But if not, since I'm recording this already, I'm gonna try to go through some of these ones. So let's start with, so pretty much the two biggest facts you're gonna know, what you need to know are the one I had up here. So the main two things, like you can do most of this knowing these two things. This, you need to know this. And then you need to know the conditional distribution. So if y is distributed as normal mu sigma, and then you partition y into y1 and y2, then y1 given y2 is distributed as normal. It always seems so stupid to do this, but whatever. Mu1 given 2 of y2, and then sigma 1 given 2, where mu1 given 2 is equal to mu1 plus sigma 1, 2, sigma 2, 2 inverse y2 minus mu2. And then sigma 1 given 2 is equal to sigma 1, 1 minus sigma 1, 2, sigma 2, 2 inverse sigma 1, 2 transpose. So if you have this fact, and then this fact up here, you can pretty much do most of the homework. So from the book, there's a couple problems. Yeah, as we talked about before, the 310, I don't know what to do about that one. Hopefully you can ask a campus wire, someone will just post that thing. I used to have the free trial for this, and then I forgot to get rid of it, and then it charged me, but then I canceled it. So, but it shouldn't be too difficult. Just remember for X, it should have a column of ones in it. So let me kind of do one that's sort of very similar to no, okay. So just to do marginal and conditional distributions. So let's say you have you have that y1, y2, y3, should as normal. Set 8, -1, 2, 3, 2, 1, 2, 1, 1, 1, 1, 7. Now, the first thing that I don't think he even said, but a marginal. So they say marginal of, for example, y1 and y3. All you need to do is just take out y2 from the equation, basically. So this is going to just be a normal of, and then you just do the things that are y1 and y3. So 8, 2, mean of 8, 2. And then again, with this, all you need to do is take like the kind of like the 1, 3 matrix out of this. So it's going to be like this, it's the 1, and then the covariances are going to be 1, or sorry, no, not this one, and this one, and then this 7 for the variance of y3. And then you're done. So that's what a marginal is. I know some people, I remember last year having trouble with that one. For conditional, you just use the formula. So if you say conditional of y1 and y2 given y3 is equal to 2, then all you need to do is follow the formula that we had. So mu of, I'm going to say this is equal to like x1. I'll just say like this is equal to like 1 to make it easier, because everything's usually written in terms of 1 and 2. And then y3 is the kind of 2. So remember, mu1 given 2 is going to be mu1 plus sigma 1, 2, sigma 2, 2 inverse y2 minus mu2, which is actually just going to be y1. Mu1 is just going to be 8, -1 plus, and then when they say sigma 1, 2, you basically take the covariances with regards to all the elements of y with all the elements of 2. So in this case, it's going to be both of them that are regards to 3. So it's going to be this, basically, and this. It's going to be plus 1, 2 would be this. Yeah, it would be this one. Sorry. I always had a professor, so I was like, just figure out the dimensions afterwards. Because I think, yeah, this is 1, 2, and this is 2, 1. So 1, 1. 2, 2 inverse is going to be this inverted. So it's going to be 7 inverse, 1 over 7. Y2, as we said, was just 2, and then mu2 is 2. So I did not mean to make that. So it's going to just be, I guess, you know what? I'll do 1, just so it's a little different. So it's going to be 8, -1 plus 1/7 times 1/7 times 1, which is 8 and 1/7. I'm not figuring out what that is. And then -1 plus 1/7 is -6/7. Okay, so that's conditional distribution. Again, that's kind of like easy one, but just in case you haven't done that in a while. With regards to 314, sorry, I know this is really far out. It's pretty much the same, just the formula that they use. The only thing that I think was tricky for some people was just this notation, if you haven't seen it before. And all it means is that when they say, like, so they have this matrix and they say it's like A and then I minus H. That just means they're stacked on top of each other. So just for reference, like A times I minus H transpose is equal to like A transpose, I minus H transpose, and so on. Is that right? Wait, I'm sure right. I'm checking to see if I got right. Sometimes you just gotta check. Yeah, that was right. Okay. Sorry that I checked that. And so on. So that's the only thing. And then also if you multiply it, you can multiply it like it's a matrix. Like you can treat this like an entry and this like an entry. So like A, B times like C, D. It's kind of like doing like well, it's not actually that's gonna work. So I should do it like this. It's gonna be like AC, AD, AB, sorry, BC, BD. Anyway, I remember people having trouble with that one too. Anyway, that's just some matrix stuff. That's pretty much the ones from the book. It shouldn't be that difficult. The other one I think is 4.5, which is just about variances and covariance between things. So again, not very difficult. Just use this matrix basically and find them. Using the formula for the covariance of beta. So remember to use this basically. Okay. I think the ones not from the book are a little trickier, so let me try to talk about them a little bit. So let me bring this over. So again, most of this homework is about using those two things from the normal distribution, those two facts on normal distribution. So 3.1 has a little bit some tricks to it. So let's kind of talk about that. In this case, we have x, which is distributed as normal, 0, 1, n. And then we have a bunch of problems finding about, well, first of all, we talk about, they ask problems saying if U for U, and if U being an orthogonal matrix, such that just means that U transpose is equal to U transpose, which is equal to I, then find the distribution of U transpose X. Again, you just use the formula, normal, 0, U transpose I, U, and then simplify. It's not really groundbreaking stuff. The next one has a bunch of stuff. This is spectral decomposition and some stuff about eigenvalues and eigenvectors and stuff. So for B, they say Y is, now we have normal 0 sigma. And they say that since sigma is a positive semi-definite matrix, which is actually true, then sigma can be broken up into spectral decomposition, which will be mu sigma U transpose. So this is true because remember, sigma is a symmetric matrix and a positive semi-definite matrix as well. Those are things to remember. Actually, I think we kind of proved that through this problem. Well, actually, I'll say that. So sigma is positive semi-definite and symmetric. That's just a fact for covariance matrices. So B says are diagonal entries of sigma positive, non-negative. So you need to use these you need to use the fact that it's positively indefinite symmetrics to show that. Can't remember. Remember also that lambda is the, so remember that mu is the eigenvectors. It's actually the orthonormal basis for the eigenvectors. Eigenspace, really. And then sigma is the diagonal matrix, the eigenvalues. Then C, you want to find the distribution of Z equals U transpose Y. Again, it's just the same thing. Normal, 0, U transpose, U sigma, U transpose, U. Simplify. Like I said, they're pretty much all the same problems. And then D and E have to do with the covariances. So D and E are saying the covariances between Zi and Zj. So for this, you need to remember that the covariance is going to be the ijth entry in this matrix, call it star. And then the other thing is that if for multivariate normal, if elements are uncorrelated, they're independent. So this is not usually the case. Typically the case is that something can be uncorrelated but dependent. But this is actually not the case. For multivariate normal, you're allowed to switch it and say that also if they are uncorrelated, they're also independent. That's just another fact about what's it called? Multivariate normal distributions. So again, we say, okay, what about A transpose Z? And now that Z is now a vector, A transpose Z is going to be normal, 0. Basically, A transpose, mu sigma, U transpose mu. A, again, simplify this technically. So again, it's kind of like the same problems over and over again. G is a little bit, so G, it's saying, assuming lambda I is greater than 0 for all I. So we assume they're greater than or equals. Now we're assuming they're greater than. Can you choose A such that variance of A transpose Z is equal to 1? Okay, so this was a little bit tricky, but so obviously this one actually being a constant if you do this because of just the way it works out, right? Like this is a matrix, and then if you do like A transpose a matrix A, that's like constant, right? It's like this kind of like the sum of the elements. So you're gonna end up getting a sum basically for this. So variance of A transpose Z is like a sum, right? So you just have to set it equal to 1, and it's going to be the elements. And remembering that sigma is just diagonal matrix, so really it's going to be the sum of the diagonals basically. Or sorry, not sigma, lambda. After simplification. And yeah, there's a lot of ways to do this one. You just have to find any way in which that they'll equal 1. So you kind of can look at the summation and figure that out from there. So it shouldn't be too bad.
Excuse me.
Yeah, what's up?
So for this part G,
yes.
Can we just, for example, form up any numbers to like put in that?
Sort of.
to
So do
make
you
it
know,
valid.
so what do you end up getting for your summation? Did you end up getting this far? Are you still working on it?
Yeah, I have already got it. I think it's
Okay.
just to make the summation equal to 1.
Yeah. So what is the summation of equaling?
Like the sum of a squared times eigenvalues.
Yeah, yeah. So I'll call them lambda I. So is this what yours
Yeah,
looks like?
lambda. Yeah, that's what I got.
Okay. Um,
Is it the final result, or do we need to like come up with some numbers to put in?
so you need to figure out a set of AIs to make this equal to 1. Um, and there's a couple ways you can do it. So you can say, so your number should probably involve, just for like, just as like sort of maybe an idea, your numbers will probably involve lambda I, right? You want to cancel out the lambda I in some way and then make it sum to 1. But yeah.
Oh, okay, I got it.
Yeah, you also can make a lot of them, you also can make some of them equal 0 if you want. So there's a lot of ways to do this. You can use n, the fact that there's n of them. You can literally can't like, yeah, whichever way you want to do it. There's like there's several answers. Like for example, um, like you could set all of them besides 1 equal to 0 and then just cancel out 1 if you wanted to, or you could set them all equal to canceling out this. So you can set them all saying like, oh, let's cancel them all these out. So root, so AI is equal to 1 over root lambda II, and that would give you a sum of AI, sum of 1 over root lambda II squared lambda II, which would equal sum of obviously lambda II over lambda II, which would be sum of 1, which would equal n, and then you can adjust it to make it so that it's not n anymore, it's 1, or you can do it different ways. Yeah. There's not like one specific answer for this. So hopefully that gets an idea in your head at least a little bit. Then H, H is like the same thing we already did again, like last time. It's the same thing basically, but they say, okay, U1 and U2 are the first 2 columns of U, which isn't really relevant, but they want you to find the distribution of 2U2 transpose Y minus U1 transpose Y, U1 transpose Y, which again, just write this as, this is really just a vector, a matrix, 2U transpose, 2U2 transpose minus U1 transpose, U1 transpose Y, and then it's the same problem. Find the distribution, it's just going to be this times sigma times, or whichever one you want, U transpose, blah, blah, blah. I suppose you could cancel some things out if you really wanted to. The other thing you could do is actually write this in terms of, you actually could write this as, if you wanted to, like -1, 2, and then a bunch of zeros, and then like 1 zeros times U, which is really like U1 transpose through UN transpose times Y, and then you could go from there. That's also an option. If you'd like. Up to you. This probably might be the better way to do it. I would recommend going with this. And this is just U. And that might cancel some more things out. Okay. Let me look at the other ones really quickly. Okay, so for 3.2, it shouldn't be too bad, especially for A, B. A, B, and C are very similar to the one we just did. And then 3.3 shouldn't be too bad. So 3.3, so we talked about, I think, the two hard ones from 3.2, and the first three are pretty easy. 3.3, there's one thing it says find that show determinant of positive semi-definite matrix is non-negative. And then the hint he gave is that determinant of AB is equal to the determinant of A times the determinant of B. And also that you can cycle through them. So determinant of ABC is equal to the determinant of BCA, which is equal to the determinant of CBA. And so what he's doing here is you can't just rearrange them anyway. You have to like kind of, it's like a conveyor belt. So like this C can come to the front. Wait, did he do this right? ABC. I don't think this one's right. Is it right? I don't think this one's not right. Because yeah, no, yeah, you're right. I copied exactly what he wrote, but yeah, it's determinant of CAB. Yeah, he got it wrong. Oh, meanie. Yeah, I was like, no. Okay, so basically for this one, remember that first of all, we also mentions the spectral decomposition. So use the spectral decomposition, and that should pretty much get you there. And also remember that, you know, positive semi-definite matrices have E values that are greater than or equal to 0. So if you just rewrite any A as equal to U transpose this U, and you take the determinant, you should be able to cycle through it and get something, and it should be pretty quick. Do not think it's very difficult. Remembering that U is orthogonal. And then the other ones are just about the covariance matrix. And I talk about finding the covariance inequality, which is basically that given some covariance matrix, that we can show that the covariance of x1, x2 is less than or equal to the square root of the variance of x1, variance of x2. And this should take you about like this should be like a 2-line proof. You just use A. So remember, covariance matrices are positive semi-definite. That's a really crucial fact. So you have the fact that covariance matrices are positive semi-definite, and we just showed the determinant is non-negative. So in B, just use those facts. And then for C, you just use it's just ask you to use this inequality to find like a successful value of ranges. So you literally just have to plug it in. Cool. Okay. Stop recording.